In the previous lecture, we have discussed the general instruction, or you can say general rule, to find the solution of second order differential equation with variable coefficient when x equal to 0 is a regular singularity of the given equation. So now today we are going to solve some of the illustrative examples so that the idea which we have developed in the previous lecture will be clear to you. So see, I have taken actually here two problems, and we will solve the first problem first of all. And this first problem, you can see we have to solve in series 2x square y double prime plus 2x square minus xy prime plus y equal to 0. So see this problem. In fact, the given equation I have mentioned again here, and you can see when we compare this given equation to the standard equation which we have discussed earlier in the general instruction, then you find that the coefficient of y double prime, which is denoted by p naught of x, in this problem it is 2x square. And so you can see if we take x equal to 0, then this polynomial p naught of x will be p naught of 0, and that will be simply 0 because x is 0. And you know, if x is at x equal to 0, p naught of 0 is 0, then x equal to 0 is a singular point of this equation 1. And we have seen that when actually x into px and x square into qx finds all ordered derivatives in the neighborhood of x equal to 0, then it is called a regular singular point. So you can check when you will find the value of x into px and x square into qx, you will see that the derivative of those functions of all orders will be defined in the neighborhood of x equal to 0. So you can say that this x equal to 0 is a regular singular point of this equation 1. So you have seen that when it is a regular singularity of this equation, then we suppose the solution of this equation in this series y equal to x to the power m into a naught plus a1x plus a2x square and so on. And in compact form, in the notation of summation, we write this solution as summation k from 0 to infinity akx to the power m plus k. Now, as in the working rule, we have seen, first of all, we find the derivative of this y. So y prime, which means dy by dx, that will be simply summation over k 0 to infinity m plus k ak x to the power m plus k minus 1. You can see this equation and simply differentiate it with respect to x. Now, we find the second order derivative of y. This is d2y by dx square, or y double prime. And you can see if you will differentiate this much, then our result will be this. It is a very simple differentiation. You can do it. Now, we will substitute the value of y, which is defined here. You can see in this equation 2, and y prime and y double prime, which we have obtained just now in the equation, in the given equation, you can say in this equation 1, actually now we will put the value of y double prime, y prime, and y prime and y, which we have defined just now. So after substituting this value, you can see the equation is 2x square y double prime, and y double prime I have obtained here. This is this much. So let us substitute the value of y double prime, and this y double prime is this much. Then the second term is 2x square minus x into y prime, and so y prime, you know, you have find here y prime. So let us substitute the value of y prime here. And then the last term is simply y, and you can see y is equal to this much. So we will substitute at the place of y this much, and that will be equal to 0. Now, in fact, we will expand this series to sum of the terms. And so let us see the first term. When you will put actually k equal to 0, that is first limit or first value of k, then see here m plus k, and k we take 0, so this will be simply m. And when here we will put k equal to 0, this will be m minus 1, and k 0, so here will be a0 x to the power m plus 0 minus 2, it means m minus 2. So you can see the first term we have written m into m minus 1 into a naught x to the power m minus 2. Similarly, we will substitute k equal to 1, and so when we will substitute k equal to 1, the term will be m plus 1 into m into a1 x to the power m minus 1. Now we will substitute k equal to 2. So when k will be 2, then there will be m plus 2, because here is m plus k, and m plus 1, because here is m plus k minus 1. So m plus 2 minus 1, that will be m plus 1. So here is m plus 1, and a2, k is 2, and x to the power m. Similarly, when you will put k equal to 3, you will get actually this term, and so on. You can take this much term or more than this. Now, the second term is 2x square minus x into y prime, and y prime is written in this manner. You can see here, this is m plus k into ak m plus k minus 1. So again, we will put the values of k equal to 0, k equal to 1, k equal to 2, and so on. So substituting those values of k, our result will be ma naught x to the power m minus 1, m plus 1 a1 x to the power m, plus m plus 2 a2 x to the power m plus 1, m plus 3 a3 x to the power m plus 2, and so on. You can do it. Now in the last term, you can see the last term is ak x to the power m plus k summation over k 0 to infinity. So again put k equal to 0, k equal to 1, k equal to 2, k equal to 3, and so on. So substituting these values, you will get actually these terms. You can see easily, and this equal to 0. Now after this, I have told you in the instruction that first of all, we equate to 0 the lowest power of x to the power m. When you will see this series, seriously, see here. When in first term we will multiply by this x squared to different terms. So in the first term, x to the power m will be there, because 2 and 2 will cancel. And in second term, there will be m plus 1. In third term, m plus 2. And so on. So in this way, in the first series, x to the power m is actually the term where x has lowest power, and that is m. Similarly, in this second series, when you will multiply by this x squared to the all terms, then in first term there will be in fact m plus 1. In second term there will be m plus 2. So all terms after multiplication by x square will contain x to the power more than m. So that is not lowest power. So here, when we will multiply by x to this first term, then there will be x to the power m, and here was also x to the power m. And you can see in the last series x to the power m in the first term, and after that x contains larger power. So you can conclude that x to the power m is actually the lowest power term. So we will equate to 0 the coefficient of x to the power m. So the lowest power of x, lowest power of x is x to the power m. You can see easily. And what we will now do, we will simply equate the coefficient of this lowest power of x, coefficient of this lowest power of x to 0. So equating to 0 the coefficient of x to the power m, we get. Now you can see in first term, what is the coefficient of x to the power m? You can see this is 2 into m minus 1 into a naught. So this will be 2m into m minus 1 into a naught. This is the coefficient of x to the power m in the first series. Now in the second series, you can see what is the coefficient of x to the power m. That will be actually m into a naught with negative sign, because we will multiply by this x to this term, then we will get x to the power m. So the second term is minus m a naught. And in the last series, you can see easily that the coefficient of x to the power m is simply a naught. So plus a naught. And this will be equal to 0. You know, from here we actually get the initial equation in m, or you can say the quadratic equation in m, which is called initial equation. And from here we will actually find the roots of that quadratic equation after solving this equation. You can see this will be simply 2m square minus 3m plus 1 into a naught. This is just a simple algebra, and this equal to 0. Now solving this equation, we will find actually the value of m. So as a naught is not 0, so 2m square minus 3m plus 1 will be equal to 0. So as you can say, a naught is not equal to 0. So what will be 0? Actually, you can see here that 2m square minus 3m plus 1. 2m square minus 3m plus 1. This will be equal to 0. And you can see I can write this 2m square minus 2m minus m plus 1 equal to 0. Now take this 2m as a common factor in the first two terms. So this will be m minus 2m into m minus 1. Now take minus 1 as a common factor, then this will be again m minus 1, and this will be equal to 0. So you can write that 2m minus 1 into m minus 1, and this will be equal to 0. So from here we will find the values of m. So when 2m minus 1 is 0, then you can see m will be equal to what? M will be equal to 1 by 2. So this is one of the roots of this quadratic equation. And again, when m minus 1 equal to 0, then you can see that m is equal to 1. So this is the another root of this quadratic equation. So you can take these two values. If we write m1 equal to 1 by 2 and m2 equal to 1. So these are actually the roots of this initial equation, or you can say the quadratic equation. Now see the nature of these roots. Actually, while we were discussing the general instruction to solve such type of problems, we have seen that if the two roots are unequal and they are not differing in integer, then what type of solution actually we will follow, we will see later. So that is the case when m1 and m2 are different. So you can see here m1 and m2 are not equal, and difference of m1 and m2 is not equal to integer, because that will be in fact 1 by 2, that is a fractional number. So the first case which we have actually discussed in the general instruction, that will be adopted to get the solution of this equation. But before that, I have told you in general instruction that we again equate to 0 the coefficient of higher powers of x. So now we have considered first of all the coefficient of x to the power m, then the next term will be containing x to the power m plus 1. So now we will equate to 0 the coefficient of x to the power m plus 1. So equating to 0 the coefficient of x to the power m plus 1 we get. When actually we will equate this term to 0, what will be our result? So see first of all here. Now we are considering the term containing x to the power m plus 1. So you can see here that this in the first series, this first term, when you will multiply by this x square to x to the power m minus 1, you will get x to the power m plus 1. So actually these 2 into this much, m1 plus m plus 1 into m into a1, this will be the coefficient of x to the power m plus 1 in first series. In second series, again you can see when you will multiply by this 2x square to the first term, then power on x will be m plus 1, because this 2 plus m minus 1, that will be m plus 1. So coefficient will be actually 2ma naught. And in the last series, you can see here directly we have a term x to the power m plus 1, and its coefficient is a1. And apart from this, when we will multiply this x to this term, you can see here x into x to the power m, that will be also x to the power m plus 1. So here coefficient will be minus m plus 1 into a1. So when we will associate all these coefficients of x to the power m plus 1 and equate to 0, so you can now write what will be our equation. So you can see this will be 2m. I have explained all the terms, so you can now write 2m into m plus 1 into a1 plus 2m a naught minus m plus 1 into a1 and plus a1, and this will be equal to 0. Now simplify this LHS to some extent. You can see that 2m into m, this will be 2m square, and here also is in fact a1. So we will combine or associate these two terms containing the coefficient a1. So what will be actually this? This will be 2m square plus m plus m. You can see in fact this a1 and a1, this will be in fact 2a1, and so here is actually 2m into a1, and so m a1, here will be m into a1 will be actually minus, and here m into a1 is plus. So m into a1 will cancel out, and our result will be 2m square plus m into a1 and plus 2m a naught. You can see, and this will be equal to 0. Now we can take one of the m as a common factor. So here will be 2m plus 1 into a1 plus 2a naught, and this equal to 0. Now again you can say that this m which we have actually obtained, you have seen that m is either 1 by 2 or 1. So m is not 0. M has two values and both are non-zero. So definitely this bracketed term will be equal to 0. So you can say that this implies 2m plus 1 into a1 plus 2a naught, this is equal to 0. And from here you can say that m is not equal to 0 here, and so I have equated this much equal to 0. And from here you can easily found the value a1 equal to minus 2 over 2m plus 1 into a naught. So actually a1 has been obtained in terms of what? In terms of a naught. I have told you earlier in the general instruction that we will actually obtain the values of a1, a2, a3 and so on in terms of a naught. So first coefficient a1 has been obtained here in terms of a naught. Now to get the value of a2, now we will equate to 0 the coefficient of x to the power m plus 2. So equating to 0 the coefficient of x to the power m plus 2. First of all, we have equated the coefficient to 0 of x to the power m, then x to the power m plus 1. Now we are equating the coefficient of x to the power m plus 2 to 0. So you can see again the terms containing x to the power m plus 2. So you can see when we will multiply by this x square to this term, you can see here is x to the power m, and when you will multiply by this x square, the power on x will be m plus 2. So coefficient in first series of x to the power m plus 2 will be 2 into m plus 2 into m plus 1 into a2. So first of all, write this. This will be 2 into m plus 2, you have seen just now, m plus 2 into m plus 1 into a2. Now see the second series. In second series you can see when we will multiply by this 2x square to this term, then x will have a power m plus 2. So one term will be 2 into m plus 1 into a1. And again, when we will multiply by this minus x to this term, here already x has a power m plus 1, and when you will multiply by this x, then there will be x to the power m plus 2. So second term will be in fact minus m plus 2 into a2. Minus m plus 2 into a2. So first of all, write this. So you can see the second term will be minus m plus 2 into A2. Now again we will see here this term you can see here in this I have written already 2 into m plus 2, and when we will multiply this m plus 1 into a1 into x to the power m by this 2x square, then again we will have x to the power m plus 2. So this coefficient will be 2 into m plus 1 into a1. So now write this. So this will be plus 2 into m plus 1 into a1. 2 into m plus 1 into a1. Now see the last series. In last series already this term is present containing x to the power m plus 2 and its coefficient is a2. So the last term will be plus a2 and this will be equal to 0. Now we will simplify this equation to some extent. So you can see here this is 2 into m plus 2 into m plus 1 a2, and here is also in fact a2. So let us first of all see these two terms. In fact m plus 2 into a2. If you take m plus 2 into a2 as a common factor, then what will be our result? You can see m plus 2 will be taken as a common factor, and a2 also will be taken as a common factor, and here is also a2 in fact. So here will be in fact 2m plus 2. Multiply this 2 to this m plus 1, so this will be 2m plus 2, and a2 is m plus 2 has been taken as a common factor, so here will be only minus 1. Sorry, this will be minus 1, and common factor will be a2. Common factor will be a2, and plus this much, that is a2 here, and this is an independent term. This is 2 into m plus 1 into a1, and this equal to 0. So now you can see this 2m plus 2 minus 1. It means this is 2m plus 1 into a2. So you can see this is m plus 2 into 2m plus 1, 2 minus 1, 1, and into a2. Sorry, here m plus 2 is multiplied only in this, not in this a2. So this is a2 and plus a2, and plus 2 into m plus 1 into a1, and this equal to 0. So when actually we will multiply by this m plus 2 to this factor, and then we take this a2 as a common factor, then what will be our result? You can see this will be in fact 2m plus 3 into m plus 1 m plus 1 into a2 and plus 2 into m plus 1 into a1, and this will be equal to 0. Now this m plus 1 is common in both of the terms, and you know m plus 1 cannot be 0 because m is either 1 by 2 or 1. So m plus 1 is not 0. So let us take this m plus 1 as a common factor, and as in RHS there is 0, so that will be removed. And what will be our result? This will be simply 2m plus 3 into a2 plus 2a1, and that will be equal to 0. Why? Because I have told you that m plus 1, which is a common factor, this is not equal to 0 because you have seen that m is either 1 by 2 or 1. So m plus 1 is not 0. And from here you can easily find the value of a2 in terms of a1. So what will be this? This will be minus 2 over 2m plus 3 into a1. But see, we have already calculated the value of a1 in terms of a0, and I have told you earlier that all the coefficients a1, a2, a3 and so on will be obtained in terms of a0. So now let us substitute the value of a1 in that equation, and you can see here a1 is minus 2 by 2m plus 1 into a0. So we will substitute that value of a1. So this is minus 2 by 2m plus 3, and value of a1, again see that this is minus 2 by 2m plus 1 into a0. So this is minus 2 by see here 2m plus 1, 2m plus 1 into a0, minus 2 by 2m plus 1 into a0. So what will be this a2? Now you can see this a2 will be equal to, this minus minus will be plus 4 over 2m plus 1 into 2m plus 3 into a0. So we have obtained the value of a2 in terms of a0. Now to get one more coefficient, that is a3, now we will equate to 0 the coefficient of x to the power m plus 3. So equating to 0 the coefficient of x to the power m plus 3, we get what actually we will get. You can see x to the power m plus 3. See here, when you will multiply by this 2x square to this term, you can see here already there is x to the power m plus 1, and when you will multiply it by x square, power on x will be m plus 3. So the first coefficient, first term in the first series, or coefficient of x to the power m plus 3 will be what? 2 into m plus 3 into m plus 2 into a3. So first of all we will write it. So this will be 2 into m plus 3 into m plus 2 into a3. Now again see, we have in first series there will be no other term containing the power x to the power m plus 3, because all other powers will be either less than m plus 3 or greater than this. So now see the second series. When you will multiply by this 2x square to this term, you can see here, then x to the power m plus 3 will be obtained. So the second term will be 2 into m plus 2 into a2. So we will write first of all it. So this second term is 2 into, we have seen just now, m plus 2 into a2. Now again see, in second series there will be actually another term containing the power x to the power m plus 3. You can see, when you will actually multiply by this x to this term, see here, then x to the power m plus 3 will be here, because here x to the power 1 is in this term, and here is x to the power m plus 2. So that will be x to the power m plus 3. So what is the coefficient? This coefficient is simply due to this minus, this will be minus m plus 3 into a3. So this next term will be minus m plus 3 into a3. And now see the last series. In fact, choosing the coefficient in last series is very easy, because there is no other factor to be multiplied. So here this term already contains x to the power m plus 3 and its coefficient is a3. So we will add this a3, so plus a3, and this will be equal to 0. So this result has been obtained by equating to 0 the coefficient of x to the power m plus 3. Now we will actually simplify this result. There is a lot of algebra, you can do it, and you can see when actually we will combine the terms containing a3 and this a3. When actually you will combine all these three terms, you will get that this is 2m square plus 9m plus 10 into a3, and this is a single term, so plus 2 into m plus 2 into a2, and this will be equal to 0. Now when you will actually factorize this, you can write this as 2m square plus 5m plus 4m plus 10 into a3, and plus 2 into m plus 2 into a2, and this equal to 0. So now see here, in this first two term we will actually take m as a common factor, and in second term we will take 2 as a common factor. So what will be our result? You can easily see that this can be written as 2m plus 5 into m plus 2 into a3, and plus 2 into m plus 2 into a2, and that will be equal to 0. Again, we know that this m plus 2 is a common factor, and you know m plus 2 cannot be 0. We have seen that m has two values, 1 by 2 and 1. So if we take m equal to 1, then this will be not 0. If we take m equal to half, then it will be not 0. it means m plus 2 is not equal to 0. So if it is not 0, then what will be 0? Actually then 2m plus 5 into a3 and minus 2a2, that will be equal to 0. Sorry, not minus but plus. So you can see that this a3 will be what? This will be minus 2 over 2m plus 5 into a2. But you have already calculated the value of a2 in terms of a0. So let us substitute the value of this a2 from here in that equation. So this is actually 4 divided by 2m plus 1 into 2m plus 3 into a0. So let us substitute it. So you can see this will be minus 2 over 2m plus 5. And we have seen that this a2 is what? a2 is 4 divided by 2m plus 1 into 2m plus 3 into a0. So this will be minus 8 divided by 2m plus 1 into 2m plus 3 into 2m plus 5 into a0. And in this way you can find the all other coefficient like a4, like a5 and so on. So we can get all other values. So there is no need to find all such values. Now we will see what will be the solution of this equation. So as you have seen that we have calculated the two roots of the initial equation, and in this case we will have actually two independent solutions, and after getting those two independent solutions we will linearly combine the two solutions, and then we will get actually the complete solution of the given differential equation. So now let us see, when m is equal to half, we are taking the value of first root of the initial equation. M is equal to half. Actually when m will be equal to half, then what will be the values of a different coefficient? You can see a1 equal to what? a1 is equal to, you can see here, a1 is minus 2 by 2m plus 1 into a0. So let us put here m equal to half and then simplify. You will get the value of a1. So in this condition you can see when m equal to half, then actually a1 will be equal to, you can do it, this will be minus a0. And what will be the value of a2? You can see the value of a2 is this much, and we will put m equal to half. So when you will put here m equal to half, here m equal to half, and simplify, then you can find the value of a2. I am write it directly here. So a2 will be in fact in this condition a by 2. Sorry, a naught by 2. A naught by 2. And similarly, when you will find the value of a3, putting m equal to half, you will get this is minus 1 over 6 into a naught. And in this way you can get the other coefficient too. So now we will write the first solution. So the first independent solution. First independent solution is, you have seen that solution in general is what? X to the power m into a naught plus a1x plus a2x square plus a3x cube and plus so on. I have mentioned it earlier. This is the general solution. Now, in this case, m is equal to half and all the coefficients a1, a2, a3 contains this a naught. So we will take this a naught as a common factor and we will substitute half at the place of m. So this will be a naught into x to the power half. Now see, a naught has been taken as a common factor. So a naught at the place of a naught there will be 1 and a1 is equal to minus a naught. So here will be only minus x and plus a2x square. a2 is a naught by 2 and you have taken a naught as a common factor. So this will be 1 by 2 x square. And a3, this is minus 1 by 6 a naught. A naught is common. So minus 1 by 6 will remain here. And so this is minus 1 by 6 x cube. So this is the first independent solution and we write this first solution by y1. So we write it y1 for convenience. And so see, this is the first independent solution. Now to get the second independent solution, we will substitute the second root of the initial equation, that is m equal to 1. So when m equal to 1, then when m will be 1, then again we will find the values of different coefficients in terms of a naught. Then you can see what will be the value of a1. See this result for a1. You can see here a1 is this much. So when m is 1, so in denominator here will be 2 plus 1, that is 3. So this will be minus 2 by 3 a naught. And when you will put m equal, this is in fact a1. So a1 will be equal to minus 2 by 3 into a naught. Again we will find the value of a2. So for this you can see the result for a2. a2 is this much and we have to put m equal to 1. So this will be 2 into 1 plus 1, that is 2 plus 1, that is 3. So this will be 3 and this will be 5. So this will be 4 divided by 3 into 5. 4 divided by 3 into 5 a naught. So this will be 4 divided by 3 into 5 a naught. And you can write it as 2 square by 3 into 5 into a naught. Here you can think that this is 2 to the power 1 and here there is 2 to the power 2. Similarly, you can find the value of a3 and for this you can see this value a3. Here m will be 1, m will be 1 and m will be 1. So this is 2 plus 1 3, this is 2 plus 3 5, this is 2 plus 5 7. So there will be 3 into 5 into 7 in denominator and you can see that this will be minus 8 divided by 3 into 5 into 7 into a naught. and this can be written as minus 2 cube by 3 into 5 into 7 into a naught. Although I have calculated the coefficients value up to a3, a1, a2, a3 we have calculated. But by induction, if you want to write the value of the other coefficient, you can write by induction. So if we want to write a4, what will be the result? You can see a1 is negative, a2 is positive, a3 is again negative. So a4 will be positive. And as you can see, here is 2 to the power 1, here is 2 to the power 2, here is 2 to the power 3. So here will be 2 to the power 4. And in denominator, you can see 3 into 5, 3 into 5 into 7. It means this is the product of odd numbers. So here there will be 3 into 5 into 7 into 9 into a naught. By induction we can write. In this way you can find the other coefficient too. So there is no need to write so much coefficients. So now the second solution you can now write. Second independent solution, you can say what will be the second independent solution. So the second independent solution. Second independent solution is, if you write this second solution by y2, then again I am repeating that solution is given as x to the power m into a naught plus a1x plus a2x square plus a3x cube plus so on. Now in this case you have seen that this m is equal to 1. So actually we will put here m equal to 1, and the values of a1, a2, a3 all coefficients contain actually a naught. You can see here a1 contains a naught, a2 also contains a naught, a3 also contains a naught. So we will take this a naught as a common factor. So a naught into x to the power m, but m is 1, so this is x. And as you have taken a naught constant, so the first term will be here 1, and minus, you can see a1 is minus 2 by 3 a naught, and a naught is common. So this will be actually minus 2 by 3x. And when you will substitute the value of this a2, and you have seen that a2 is 2 square by 3 into 5 into a naught, and a naught is common. So this much square, and minus 2 cube, you can see the value of a3, 2 cube divided by 3 into 5 into 7, and a naught is common, and x cube, and plus so on. So this is actually the second independent solution of this differential equation. As you can see, these solutions defined either in A or in this B contains only one arbitrary constant a naught. Only a naught is as an arbitrary constant. So, and the equation is of second order. So you know, if a differential equation is of second order, there must be actually two arbitrary constants. But these independent solutions contain only one arbitrary constant. So separately, these two independent solutions cannot be the complete solution of this equation. And you know, to get the complete solution, what we do? We simply combine these two independent solutions linearly, and then we get the complete solution. So hence the complete solution is the linear combination of y1 and y2, which is, and this linear combination we can write y of x equal to c1 y1 of x and plus c2 y2 of x. Here actually c1 and c2 are the arbitrary constants. So you can see we know the value of y1 and value of y2. So after multiplying by c1 and c2 and adding them, we get the complete solution. So you can see what is y1. So c1 and y1 you can see is this much defined in this equation A. So this will be c1 a naught x to the power half. c1 a naught x to the power half. And inside the square bracket there is 1 minus x plus half x square. 1 minus x plus half x square. And minus 1 over 6 x cube. Minus 1 over 6 x cube. And plus so on. And plus c2 y2 of x. See here the value of y2 of x. This is a naught into x into 1 minus 2 by 3 into x plus 2 square by 3 into 5 into x square minus 2 cube by 3 into 5 into 7 into x cube plus so on. And as c1 and a naught both are constant, so product of c1 and a naught will be some another constant. Similarly, c2 a naught will be some another constant. And if we write these constants as the product of c1 and a naught as a, then this will be a into x to the power half into 1 minus x plus 1 over 2 x square minus 1 over 6 x cube plus so on, and plus b. b means c2 a naught into x into 1 minus 2 by 3 into x plus 2 square by 3 into 5 into x square minus 2 cube by 3 into 5 into 7 into x cube and plus so on. So this is actually the complete solution of that differential equation. Actually, I have mentioned earlier two problems, but I have solved the first problem in this lecture only. In fact, the solution of second problem will be done in the second lecture, because the time length of this lecture will be very large to solve that question in this lecture. So definitely I will solve that problem in the second lecture. So watch my video and you will find the solution of the second problem in the another lecture.